We are doing roots of complex numbers. Just to recap, if we find the roots of complex numbers, we must not confuse it with the Marvis theorem when we find the power of a complex number. For that, we will use the Marvis theorem. But when we find the nth root of a complex number, we will use this very important formula. The nth root of the complex number is r to the power of 1 over n, e to the power of I theta over n, e to the 2k power over n. So make 100% sure you understand the difference between these two branches. This one will be to the power of 5. Here, they will ask you to find the nth root. If they ask for the fifth root of 1, remember that it is not z to the power of 5. It's the nth root. And just to recap, a lot of students get this wrong. They will sketch the whole thing on the Argand diagram, but we're not supposed to. We will always sketch the inside. We are getting the nth root of the inside. Hence, we always sketch the inside. So here we will sketch z equals 1, but we know z equals 1 is on the x-axis. So if 1 is there, it must mean that our radius is just 1 and our theta is 0. So just to recap, always remember on the x-axis, positive x-axis, we have theta 0. Positive y-axis, we have theta pi over 2. Negative x-axis, theta pi, and negative y-axis, theta 3 pi over 2. So just to stress this situation, if you get the nth root of 1 plus 3i, you're doing the fifth root. So what we're going to do in this lesson, we're going to use our very important formula, and we will always solve r and theta first. And then you will see the other question that they can give, an alternative question. They can either ask solve for z in this equation or factorize. So for both, you can write z to the 4 as minus 16i. So in other words, you're finding the fourth root of minus 16i. So just to recap what I said earlier, students often go wrong. They want to sketch the whole thing on the Argand diagram. No, we will just sketch the inside. And just to recap, minus 16i will lie, we're doing the Argand diagram, so this is your real and imaginary part. Minus 16i will lie on the negative y-axis. In other words, this radius is 16 and theta is 3 pi over 2. This flow diagram, very important for what is coming. So we will do 2 examples. First, we'll do an easy example, and then after that, we will try to do a more complicated one. So, just to recap again, for nth root, we're going to use this formula. If they ask you find the complex roots of of the 4 complex roots of z equals negative 4, we find the 4 roots, the 4th roots of negative 4. Just to recap what I said earlier, do not confuse that with the Marvis theorem. So they can also ask it differently by asking to factorize, in which case we will also get z by itself. So in other words, we're going to find the 4th root of negative 4. So be careful, do not sketch the whole thing, just sketch the inside is our complex number. So negative 4 lies on the negative x-axis. Just to recap, remember negative 4 as a complex number is negative 4 plus 0i. Hence our x negative 4 and our y 0. Since we have negative 4 here, we see that our radius is 4, radius always positive, and theta is pi. Why is theta pi? Because we are working in the second quadrant. So, for the 4th root of negative 4, we see that we're going to use this formula r 1 over n ei theta over n e to k pi I over n, where n is equal to 4, theta is equal to pi, r is equal to 4. Very important, since we are doing the 4th root, we will get 4 roots, but we will get k's at 0, k at 1, k at 2, and k 3. So let's start with this. So I'm going to substitute everything now that I have mentioned here into my formula, which I want you really to study before you start with your examples. So in this case, we are going to have 4 to the power of 1 over 4, r and n, e to the power of I theta pi n 4, and e to the 2 k pi I over 4. But since k is 0, we substitute k with 0, e to the 0 is 1, we can take that term away. So, just to recap, this will be equal to 2 squared to a quarter, and then very important, e to the I pi over 4. Let's write it here. E to the I pi over 4 is cos pi over 4 plus I sine pi over 4. But by now you all know your special angles. Cos of pi over 4, 1 over root 2, and sine of pi over 4 is also 1 over root 2. Hence, for this answer, let's move that down. For that answer, we will have square root of 2. This is our square root of 2. And then e to the I pi over 4 will be cos pi over 4 plus I sine pi over 4, which will be 1 over root 2 plus I 1 over root 2, and our final answer is 1 plus I. So just make 100% you understand every step that I have done there. Now Something that we will do and stress later. If a polynomial has real coefficients, the non-real solutions will occur in conjugate pairs. Let's look at our polynomial z4 plus 4. Just recall that 1 is a real coefficient and the constant is also a real coefficient. Lots of students often get that wrong. They forget that the constant is also a coefficient. So since we have real coefficients, our roots will be in conjugate pairs. So just to see if you understand, we are going to have 4 roots. So in conjugate pairs, we know that 1 plus i's conjugate is 1 minus I. So the first root will be here, where we have 1, 1. The second root is in conjugate pair, will be here, because we will have 1 minus I. Now, why I say Z3? Because this is k equals 0, since our angle is an acute angle. So we know we are working in the first quadrant. So we will check now, but K1 and K2 will be conjugate pairs, and that's why I made this K3. So I don't have to work out K equals 3. I will now straight go to when K is 1. So I'm doing Z1. Let's substitute into our formula. We will have theta, which we worked out as pi, n is 4, e to the 2k pi I over 4. Now we substitute k is 1, we get square root 2. Remember we said I pi over 4 is 1 over 2 plus 1 over 2i. Now, what is going to happen here? K is 1. So, since k is 1, we will get e to the 2 pi I over 4, which is just e to the pi I over 2. Now, just to recap, e to the I pi over 4, let's just check e to the pi I over 2. You can study that one. It's cos pi over 2 plus I sine pi over 2. Cos pi over 2 is 0. Sine pi over 2 is 1. So for this answer, we just get I. So therefore, we just have an I there, and if we multiply that out, we will just get minus 1 plus I. So just recap, when k is 0, we had 1 plus I, but since the coefficients are real, our roots are in conjugate pairs, so we immediately know that 1 minus I was also a root. Now we did k equals 1, so we're doing Z1. We got minus 1 plus I, and since our roots are in conjugate pairs, our last root will be 1 minus I, and there we have our 4 roots. So I hope you understand this question well. So just to recap, if a polynomial has real coefficients, just remember that a constant is also a coefficient. The non-real solutions, if any, will occur in conjugate pairs. Obviously, a real solution can't have a conjugate. Okay, there's our formula again that you're going to study well. Now, the next question, which is slightly harder, they can ask it different ways. They can say factorize, but in any case, when you factorize, you know that you're going to get z by itself. So you're going to rewrite it as that. So even if you have to factorize, please remember that you are still going to get the roots. Like I did in my flow diagram, I said even if you get solve or factorize, you will still get the nth roots. So let's recap, do all our steps again. First, we'll do that. Now, secondly, we will sketch. What will we sketch? The inside function. Please remember that because we are getting the fifth root of a, and a is our complex number. Like I said a couple of times now, students do often make a mistake doing that. You want to sketch the inside. So that means that x is 1 and y is root 3. So we're going to find r and we're going to find theta. But remember what I said, it's very important which quadrant we're working in. Hence the fact that I am sketching. So my r, just to recap, will be the real squared plus the imaginary squared. In our case, it will be 1 squared plus root 3 squared, which is square root of 4, which is 2. So we know that r is 2. Finding the argument, so remember this is called the argument of our complex number. In this case, let's rather call it a. And how do we find the argument? Since it's in the first quadrant, we can just go straight. Theta is arctan y over x, where x is 1 and y is root 3. So we have arctan root 3 over 1. Now, like I said before, very important you know your special angles. I see that a lot of students are still using the fan from school, but I prefer doing these because at this stage you should immediately see arc of tan of which angle is root 3, and you see it is pi over 3. So I'm not going to waste time with this. This is all first year work. So here I see theta is pi over 3. So just never mention the degrees. It's standard globally to use radians. Now I'm going to my lovely formula, recalling that my n is 5. Why is my n 5? Since I am doing the fifth root of my complex number. Now recall that k will be from 0 to 4. So we are going to find zk. We know now that our r is 2. We know that our r is 2 and our n is 5. We know that our theta is pi over 3. Pi over 3 over 5, 2k pi I over 5. Very important. If we even want to simplify this, so we have the fifth root of 2. Here we can just say pi over 15. So I'll just explain it just now. And here we can just say 2k pi I over 5. Just to recap this from school, often students do not know how to just do it straight away, since all of you were allowed calculators in school. But remember, the quickest way, let me rather do this. If you have A over B over C, you can just drop that B to the bottom. So just remember this. We shouldn't really spend time on it since it's school, but like I say, often students make a mistake like that. So here we have now our zk that we are going to work with to get the 4 different roots. The 5 different fifth roots. So we will first start with k equals 0. Substitute it into my formula. I get the fifth root of 2 e I pi over 15 e to 0 pi I over 5. This part we know is 1, so we can remove it. So there is our first root. And since pi over 15 is not a special angle, we can leave it like that. But how do we know when we sketch the roots that this is in the first quadrant? It is pi over 15 is an acute angle. So pi over 15 is an acute angle since the denominator bigger than the numerator. Pi is 3.14, so you know it's an acute angle. And then very important, just to recap from earlier, if a polynomial has real coefficients, just reminder that does include the constants, then the non-real solutions will occur in conjugate pairs. But let's look at our question. Do we have real constants? Yes, here we have. Yes, here we have. But that is not real. So we will not have our roots in conjugate pairs. So we cannot assume that another root will just be the conjugate. Definitely not. So we're going to have to go through all 5 of them. If k is 1 and I am substituting, just recall that I am substituting every time into my formula. So I will get ei pi over 15. So obviously that's going to stay the same. But now k is 1. So I will get 2 pi I over 5. And since my bases are the same, also from school, I will add the exponents. So what will I get? My LCD is 15. So I will get 7 pi I over 15. Are we still in the first quadrant? 7 pi over 15. You can check that on a calculator, but I know at most universities we are not allowed to use a calculator. But when I sketch it, I will just explain how we also know which quadrant to work in. Now we are going to, when k is 2, I'm substituting again. The first part stays the same. Then I have e. My k now is 2. So I have 4 pi I over 5. And my bases are the same. I am adding. Let's see what we will get here. We will get times 3 is 12. We will get 13 pi I over 15. Okay, so just remember, very important, that I am using this formula all the time. I'm basically just replacing k. So my next one, we are confident that these stay the same. We just now replace k with 3. 2 times 3 is 6. So we get 6 pi I over 5, not 15. Our bases are the same. We add the exponents. We will get 19 pi I over 15. And then the last one, we'll just do that one quickly. You replace k with 4. I get e to the 8 pi I over 5. So what do I get? I will get 24, 25 pi I over 15. But we can simplify that fraction since 5 goes into 15 and 3, I will get this answer. So just remember always to simplify in maths where it is possible. So let's look at our 5 roots. We have first one, second one, third, fourth, and fifth. And just remember that they are not in conjugate pairs, since our coefficients, that is including our constant, is not a real coefficient. So that is the end of part 1. In part 2, what we will do, we will try to write a fraction. We will split it into partial fractions using our nth roots formula. So that's the next one. If you need any more notes or have any questions on the video, you are welcome to email me at Dr. Brooks or at universitymaths.co.za. So if you have any questions about the video, unfortunately not maths questions, but any questions about the video, or if you need to order more notes, you are welcome to do so. And that is the end of Roots of Complex Numbers, part 1.